Okay, as part of this, project that we're doing in the class this semester, we're doing the deck design problem, which starts in chapter 2, so we may as well start talking about things now. You've already got I emailed you out that sort of like overview document of, hey, this is what the lab's all about. But what it's trying to do is there's going to be certain chapters at the end of the chapter which start which talk about pieces of this lab. And the first chapter is chapter 2. And in chapter 2, we're talking about forces and how they act on bodies and so on and so forth. So what's a real situation where forces act on bodies? Well, it might be like a residential deck. Okay, so you've got the layout of this regular deck. It's 16 feet wide, it's 20 feet long. It's got so many pounds per square foot on it. What I would like to talk to you a little bit today is sort of like a precursor to all this, is actually section 210 in your book, which is 2+ pages long, which talks about load paths. Okay? And a deck is a type of floor system. A lot of our buildings have floor systems in it. A lot of our buildings have roof systems in it. A lot of our bridges have decks on them. So we want to talk about load paths in structures. And when they talk about a load path, what they're really talking about is the path that a load takes to ultimately get down to the foundation and ultimately into the ground. Okay? I mean, that's, if you think about our structures are no more elegant than just vehicles, if you will, to take loads and put them into the ground. We just got to make sure that happens. If one little part fails, then the structure falls down, or that piece of the structure falls down. That's no good. All right, so a load path, just how loads get from point A to point B to point C to ultimately down into the ground. All right, so that's what a load path is, and what I'd like to talk to you today about is and this is section 210 of the book, but just some general concepts of load analysis and structures. We have many times a floor system, and the floor system can be held up by beams. Okay, now a lot of times in our line of work, we like things to be evenly spaced. Doesn't happen all the time, but a lot of the times for our structures, we like beams. When we look at a framing plan, we like them to be evenly spaced. Okay? So like here, I might have, maybe these are steel beams. Okay? And, maybe they're 6 feet apart. Maybe the floor that you're sitting on has beams below it, and they're at a certain spacing. Okay? If you have wooden joist, spacing is going to be smaller because wood's not as strong as like maybe steel. So maybe in steel you have 15-foot wide spacing. It varies. It depends what the structure is and what the members are. But what I'd like you to think about is if I put a floor loading over here, and I say the total floor load is 500 pounds per square foot. I say the total floor loading is 500 pounds per square foot. What that means is if you look at like the 1x1 tiles on the ground, every one of those carries 500 pounds, right? And these are parallel loads, and we just got done talking about parallel loads. Well, think for a minute, if you will, about this beam right here. What does this beam have to do as far as carrying its fair share of the load? What this beam has to do is it has to carry half the load between it and the next member to its left, and half the load between it and the next member to its right. So this member, if these were 6 foot spaced, 6 foot on center spacing, it would have to carry 3 foot this way, and it would have to carry 3 foot that way. So this beam would have to end up carrying 6 feet of the floor, or 6 feet of the roof, or whatever this framing plan was on. What would this edge beam, if this was an edge beam here, how much would it have to carry? Just 3 feet, because there's nothing to its left. It just has to carry 3 feet. Well, let's go back to this interior beam. Okay? That's what they call this concept right here, of looking out to your right and saying, if you were the beam, I'm going to carry half of all the load between me and the member to my right, and then look to the left, half the load that way. Okay? That concept right here is a concept that they call tributary width. Okay? And some people call this distributive width. So you could get into a different, you can hear called 2 different things. But that's the basic concept. If I'm a floor joist or floor beam, bridge beam, roof beam, girder, whatever, I'm going to carry half the load between myself and the member to the right of me. I'm going to carry all the load halfway between myself and the member to the left of me. That's what I'm responsible for. Okay? Now everybody realizes they're looking down at a sort of a floor plan, a plan view of this floor, right? But what if I looked at this beam in just 2 dimensions? And let's say it was supported by something out on this edge, and it was supported by something over on this edge. Well, the beam might look like this. How much load, since I'm only looking at it now in 2 dimensions, how much load am I going to say is on this beam now? Is it 500 pounds per square foot? No. We'd like to start talking about this load, this uniform load, in terms of maybe pounds per foot. Because, now my beam's got a certain length, right? So what is it? It's not per square foot, that's area. This is where we're looking at area, right? Here we're looking at per foot. So what if this was carrying 6 feet of distributive or tributary width, and each square foot was 500 pounds per square foot, 500 pounds for every square foot, and I've carried, how much load is being carried just on, if this was a 1 foot strip right here? Every square foot's 500 pounds per square foot. And how many square feet do I have in here? 6. So how much load am I carrying per foot? 3,000. So the 500 pounds per square foot times the tributary width gives me a uniform load of 3,000 pounds per square foot. Okay? And so that's going to be very useful for us when we go onwards. Okay? That's actually what they call a little free body diagram, but we'll talk more about that in chapter 3. But anyway, if I asked you, how much load does this in total does this beam carry? What would you tell me? Well, you'd say, what's the length? The length's, let's say it's 20 feet. Okay, 20 feet times 6,
60,000.
Yeah, well, that's 120 square feet. Yeah, times 500 pounds per square foot. Yeah, there you go, 60,000. So that would be total. That would be the whole beam is carrying that. But a lot of times we like to express that in per foot units. Okay? So anyway, that's going to be important as you start. Chapter 2 sort of does this, starts having you consider tributary width and how things behave relative to load path on, on structures. So that's a real basic concept.